So I think next up is Houjun Tang at Lawrence Berkeley also. And Tang is going to talk about specifically this asynchronous IO wall connector that I mentioned in this. And if he's ready, that's great. Take it away, Tang.
Okay, thanks, Quincy. Hi, everyone. I'm Houjun Tang. I work at Lawrence Berkeley Lab. And today I will be talking about our work on the asynchronous IO wall connector, which enables transparent asynchronous IO operations using background threads. So first of all, why do we want to enable asynchronous IO operations for HDF5? Well, simple answer is we want to make HDF5 applications run faster. And by default, all the HDF5 IO calls are synchronous, meaning they are blocking and will keep the application from running other tasks until the IO task has been completed. So in this way, the CPU of that application often remains idle, doing nothing at all, just waiting for the IO. And we want to change that with the support for asynchronous operations, where we can have the application to continue working on other tasks and overlapping the IO time and compute time or communication time, such that we can speed up the application like this little figure I have on the screen. So with that side, the async IO wall is implemented as a wall connector, as Quincy mentioned. So async wall is a pass-through connector, and meaning that it can be stacked upon other pass-through connectors, such as the caching wall, which Hui will introduce in the next talk. And I think Quincy mentioned a lot about the wall infrastructure, and so the asynchronous IO wall would just function as a wall connector, and it will, by default, it will call the native wall to operate on the HDF5 files, but it can be stacked with other walls and then call other terminal wall connectors. So a little bit more about how to enable the asynchronous wall. So there are two ways, or two modes. One we call implicit mode, and the other is explicit mode. So by implicit mode, it allows the HDF5 applications to not change anything at all in their code. So they can just use the compile the asynchronous IO wall and set a bunch of environment variables, and magic happens. Many of the HDF5 IO operations will be executed asynchronously, and thus the application will benefit from the async IO overlapping the time with the compute or communication. So the way to enable this, Quincy also showed earlier, is just to set some two environment variables. One is to specify the wall connector to be async, and if you do not need to stack it upon other wall connectors, you just specify under wall equals to 0, meaning it will use the native wall. And if you want to stack others, you just specify this and specify the corresponding information of the other wall connector. And you will also need to specify the dynamic library that you compile the async wall. By default, in this implicit mode, all the data writes are non-blocking, but we do make a buffer copy to make sure that the user's buffer is not modified or frayed before the actual IO operation has been completed. And also, we make all the read operations to be blocking. So in this way, the application will not get invalid data before the async operation has finished. And the other mode, which gives more control to the user and requires some modification of the code, is called the explicit mode. So in this mode, the users can use an event set to manage asynchronous operations. So basically, the user will create an event set ID and associate the IO operations or the HDF5 calls to this event set, and manage multiple operations as a group. So, and also using the explicit mode, the user have more flexibility with the various settings of the asynchronous IO wall connector. For example, now that the user can control that to enable the asynchronous read, and also disable the buffer copying if the user knows what they are doing, and they will not operate on the buffer until they know that the write has been completed. So some code snippets. So basically, this slide shows the implicit mode where you see on the left-hand side is the application's normal HDF5 function calls, and with the implicit mode, there's no need to modify any of this code. They stay the same, but once they set the environment variable to enable the asynchronous wall, many of these operations can be executed asynchronously. So for example, all the file opens, group opens, dataset opens, and writes becomes asynchronous. And by default, the read is synchronous, and there are some other operations. There are some limitations due to the current HDF5 implementation, is that some of the calls will be executed synchronously. For example, some of the metadata get operations, like getting the data space of a dataset, will be executed synchronously, because otherwise we will not get a valid space ID. So, but most of the actual IO operations can be done asynchronously. So the next is the explicit mode. So this explicit mode, we are managing the asynchronous task with the event set. So the user first needs to create an event set ID with this new H5ES API, and then there are a bunch of new HDF5 APIs added with the underscore async added to the end of the function name, and all the other parameters stay the same. We just add an additional parameter, the event set ID at the end, to specify which event set you want these operations to be associated with. And once we are doing this, then they will all be executed as asynchronous tasks. And there are some dependencies which determines the order of that execution. I will explain a bit more in detail later. And at the end, if the user wants to make sure that all the asynchronous operations have completed, the user needs to call this H5ES wait, which basically blocks until all the operations, all the asynchronous tasks have finished within this event set. So basically, this is a synchronization point where after this call, all of the buffers can be modified or read safely because all the async task has been completed. So a little bit more on the workflow of the async wall. So basically, at the start of the application, the async wall will be initialized where we are using a background thread to execute all the asynchronous tasks. And so currently there is a limitation with the HDF5 library where the library has a global lock, which is acquired anytime when the application or the background thread enters the library call. And this limitation has presents us some challenges because it essentially, without a good management of the tasks, it prevents the asynchronous tasks to be executed true asynchronously. So for example, without proper handling of the asynchronous task, it can be happening where the application thread or called the main thread issues a HDF5 IO call, and it goes into the wall connector, and the wall connector executes that immediately, and which they consecutively acquires the global lock, and then the application thread does the next HDF5 call, and it also acquires the task which prevents the background thread to execute the task asynchronously. So if for some reason or for most of the cases, the application thread executes calls interleave with the background thread, then essentially we are having a serialized execution as each one enters the library, acquires the lock, and the other thread will wait for that lock. So that defeats the purpose of the asynchronous execution. So some careful handling was added to the library and to the async wall, is that we are doing status checking or spying on the application thread, where we queue a number of operations. We do not start executing them, but we put them in a queue and wait. When we detect that the application thread has done issuing all the HDF5 tasks, maybe it's doing the next computation, or maybe it starts to do some communication, and only then we start doing the async task background thread execution. So in this way, we avoid the interleave execution and interleave the HDF5 global lock acquiring, and we can now have the task executed in the background thread and overlapping the I/O time with the application's compute and communication time. So I will talk a little more about how we manage the different tasks with their dependency in the next slides. So the application does all those operations, and at the end, after the file close, before the application terminates, we will also do the async wall connector finalization, and we will destroy the background thread and free all the resources. So for the asynchronous task management, so we characterize all the HDF5 I/O tasks into three categories. First one is regular task, where the regular task does not have dependency on any other task. It can just be executed independently without worrying or waiting other tasks. A typical example is the file open call, where it opens the file and it does not depend on other operations, so it can be executed without considering anything else. And the next one is a dependent task. So the dependent task depends on the successful execution of other tasks. For example, read and write operations on the object of a file depends on the successful open of the file. So we manage this as a separate type of task, and we put it in as a separate list in the task queue. And the third one is a collective task. So the collective task is managed independently because of the nature of the MPI collective operations. We do not want to have the collective task in the application to be executed out of order. So we want to keep the collective task order so that all the MPI processes are executing the same task at the same time to avoid a backlog issue. And also for the collective task, any collective task will be executed without other collective tasks being executed at the same time. And lastly is the file close. So file close is also a dependent task, which depends on all the previous operations on the same file. So that's about the task management. So a little bit more on the dependency management. So we have a few rules to be enforced to make sure the data is consistent and we are doing what the application is intended. So the file create and file open operations, they must be executed first, because otherwise the rest of the operations will not make sense with the invalid file ID. And any read or write operations to the same object will be executed in the application's order of issue. So we will keep the execution order of the application and to keep the data consistency. And as I mentioned previously, the collective operations will be executed in order and one at a time. And the file close starts when all the tasks of the file have been completed. So next is the error handling. So error handling can be tricky with the asynchronous execution because even the task may fail, it will not be reported to the user immediately because it is executed in the background thread, and the error may happen while the application is doing other things. So currently, our handling of the error is that if any asynchronous operations fails, all of this dependent children will not be executed. So, in addition, we push error message to the HDF5 error stack, indicating that its parents has failed and this task cannot proceed. So the bottom part of is the error message from the error stack. So we put a new error saying that the parent task has failed to the error stack, and just telling the user that the operations cannot finish. So some evaluation. So in here, I'm showing the results of two applications. One is called Async IO, where each process writes 256 megabytes data to a dataset in the HDF5 file. And here we compare 4 different cases where the original one is in the green line. That is the original HDF5. And the dashed orange line is where we enable the async connector, but without overlapping it with any compute time. So essentially, it measures the difference between the orange dash line and green line is the overhead. And next, we measure the 2 scenarios where the application has some compute time for the IO to overlap with. The red line is where the async wall can overlap around 50% of the compute time, and the blue line is where the async operation can overlap 100%, meaning that most, if not all, of the IO costs can be hidden from the application. On the right hand is another application. This one reads the data that the VP IO writes. So similarly, we see a low overhead with the dashed orange line and green line, and we see a significant time reduction with the other 2 scenarios where we have some time for the async operations to overlap with. Next, so this one we have tested with another application with MREX framework. So this is MREX HDF5 benchmark, where we write a number of time steps of data with computation in between, and we can see our async wall connector can successfully hide the IO time from the application. And for future work, so currently we are using Algoboss as the background thread engine, and our team are in development of a thread engine called TaskWorks, and we plan to switch to that once that work has completed. So it has more functionality and that we need. So we will be doing that. And the next one is to merge compatible operations. So basically, if the wall connector is smart enough that when there are 2 dataset write operations onto the same dataset, then we can merge that into a single one and potentially speed up the IO time. And next one is using multiple background threads. Currently, we are using one background thread because of the HDF5 global lock. So once that limitation can be released from the HDF5 library, then we can utilize multiple background threads to execute multiple jobs in the background concurrently. And we have this async wall implementation in the Bitbucket. So the address is on the bottom. And that concludes my presentation. I'll take any questions.
Thank you, Tang. Let's see, we're on a break, so you've got 10 minutes to chat about these and anything else with Tang. And there's a ton of questions in the chat window if you can see it, Tang.
Yeah, I'm looking at it.
Okay. Perhaps the easy to answer one are the runs in the evaluation with the implicit or explicit.
Oh, the runs in the evaluation, they are explicit. But we still do the memory copy in all of these cases.
Okay. And then John was...
Quincy, maybe you could take a crack at my question,
Sure.
if that's appropriate.
Sure. It does look like, and so John's question is about using the async vol to lay on top of another vol that potentially might be a terminal one, a cloud-oriented storage mechanism like the RESTful vol connector. I do think that was one of the purposes for this async vol, is to, in a sense, abstract away any asynchrony that any other connector would otherwise need to go implement on their own. And that would be very helpful, I think, and just offload a bunch of development work out of other people's time, really.
Right, but
we've had that discussion with Huiho at Argonne, and he's basically, we're working our way through making the async connector not cache things, not the buffer copy, and making the node local connector that he's going to talk about shortly not do things asynchronously. So I think that's possible. Sorry.
Yeah, I don't know how that works. I mean, would there need to be some kind of capability interface to the vol to ask it, you know, do you support async for this or that or not?
Right, we've talked about that as well. We're developing introspection callbacks for the vol framework that allow an application to ask about capabilities of the vol, the connector stack that's currently noded. And then even the pass-throughs can make queries of layers below them. You know, are you thread safe was an interesting query for an asynchronous one to make query about, right? So yeah, I think there's some real potential here. It's the direction we'd like this connector to go. So let's see here. Mohammed popped in first. So how useful is the implicit mode given the delayed error reporting that might break an existing application? And memcopies. Yeah, memcopies are, like I said, we're trying to get those out of the async connector in the long run and offload them into more specifically developed caching style connectors. But from the implicit mode, it is a very optimistic mode of operation for an application. The app has to assume that life is going to get very, very bad if errors start happening. And so maybe it's not for everyone, but that's why we have the explicit mode that's still very easy to use with the event sets, bundling everything together into nice packages that you can check on as a group. I do think there's trade-offs. I think implicit also is going to have a nice, easy way for people to get in, but it won't perform as well as what Tang's showing here for explicit mode.
Yeah, another question is when the async wall, there is an error, but it has already returned an application. So I think we talking about to register the user callback functions to handle the error with the async failures.
Right. Yeah, we're trying to open up the possibility of optimistic execution, but at least exit paths off the highway in polite ways for error scenarios. Implicit mode, it'll probably be a callback that said, hey, you know what? I'm really sorry, man. But this thing I told you earlier that succeeded, it really didn't succeed. Sorry, with a callback.
Yeah, so that's what I was sort of implying, that, you know, without the user interference, without application changes, it's really hard to get the implicit mode really working. And it just opens the door for many users to just complain and saying, hey, it's supposed to be fast and works great, but what am I doing wrong? And, you know, you try to go debug, and it's going to be hard to debug without, you know, just something implicit, really. And you know, you could end up with, like, you know, thousands of calls, right? And depending on what the application.
It is potentially wild and crazy. I agree with you. But it's a valid mode for, I'm pretty confident this will be fine. You know, I'm just going to go run this execution. And we're working on the error reporting for explicit ones as well. And so the current model, like Tang was saying in the slides, is that once you get an error, that event, you won't be able to put any more operations into that event set. It's like breaking a glass jar in a sense. There we go. All right. Yeah, so once you've broken the jar, you have a bad operation, you can't put anything more in it. And the only thing you can do is look around at the operations you've got and kind of query the errors back out and kind of examine them. We're not expecting to resume or restart from an error scenario with the async connector. But we do give a lot of debug output. We worked on the infrastructure within the library so that you can receive back, and Tang showed the error stack, but you can also get a copy of the API parameters that you passed in for a failed async call, and then know much more explicitly, oh yeah, this was the group that I tried to create and it failed because it was a duplicate of something else. You know, that's at least a possible scenario for a group create. Some of this asynchrony, since Mohammed mentioned some of these things, there's a talk later on in a half hour-ish that Jerome's going to talk about the Deos Wall connector, and there's asynchrony built in there too. So there's possibility for adding asynchrony at multiple layers. Doesn't have to be a pass-through like this one that Tang's describing. It could be a terminal one that performed async operations as well. So we're on break, but I'll hang out here in 3 minutes. Unrelated questions. Is there a plan to update the Wall framework to support features only in the native library, filters, chunk caching? So I think that's up to the connector implementer themselves, I would say. Those are features of the native one currently.
Yeah, but with refactoring, do you think it would be possible to kind of facilitate this work? Because it's really too much pushing to the wall connector creators.
Well, some caching, Viho is going to talk about certain kinds of caching that his connector implemented. And other things may be pretty specific. I don't know. It's an interesting thing. We could talk about reusing those in ways that other connector authors could do. The interfaces are public, especially for IO filters. They could use those filters themselves.
Yeah, but you have to, like John, he had to implement for RESTful his own compression. So it's really re-implementation.
You could use the interface and just invoke them.
It's probably not hard, but we had like, not for walls, but for open dep, they had to implement compression and decompression because they were bringing chunks to open dep server And this is kind of similar. So they were asking what we can do to facilitate and have interfaces in HDF5 library that they can use to directly call those routines from different libraries, which will help here.
Yeah, like Dana was saying, I think with a little bit of wrapping, maybe it's possible. It's an interesting project.